Hi 11s. So today we're going to be walking through a couple of chemistry questions. So the first one is a multiple choice question. So a metal carbonate reacts with an acid. What products are made? So there are a couple of essential or common generic chemical reactions that you need to know in chemistry. And a lot of them are acid reactions or reactions involving acids. And this question is testing you on one of those. So acid plus a metal carbonate produces 3 products. It forms a salt, it forms water, and the third product is carbon dioxide. Therefore, the answer to this question is C, salt, carbon dioxide, and water. Question 2, the diagrams show different structures of carbon. Which structure is Buckminster fullerene? So in this question, we're given 4 options, and each one is a different structure of carbon. And these different structures are known as allotropes. That's the special name for them. And you need to know what each allotrope looks like. So the structure and the name for them. So structure A is diamond. Structure B is Buckminster fullerene. So that is going to be our answer. C is graphite. So graphite is quite easy to identify because graphite has layers. It's made up of layers called graphene. So this one is graphite. And the last one is a nanotube. Nanotube. The answer here is B. Question 3. Sodium is a metal in the periodic table. Use the periodic table to work out the following: the relative atomic mass of sodium, the number of protons in an atom of sodium, and the number of electrons in an atom of sodium. So on your periodic table, you will have the different elements, and you would have 2 numbers. For sodium, the 2 numbers are 11 and 23. And sometimes the bigger number is on the top, sometimes the bigger number is at the bottom. What you need to know is that the smaller number of the 2, so out of 11 and 23, 11 is a smaller number. The smaller number is called the atomic number, and the bigger number is called the atomic mass. So the atomic number can tell us a couple of different things. It can tell us the number of protons, so number of protons in an atom. It can also tell us the number of electrons in an atom of sodium in this case, of sodium in this particular case. The atomic mass tells us the number of protons and neutrons combined in an atom of sodium. So it's the total number of protons and neutrons added together. So if we go back to the question, the relative atomic mass, so that is the bigger number of the 2. So the answer here is 23. The number of protons in an atom of sodium is 11. So that's the atomic number. And the number of protons is the same. And the number of electrons in an atom of sodium. So we established earlier on the number of electrons in an atom of sodium is also equal to the atomic number. Therefore, the answer is 11. Sodium is an example of an atom that can form an ion. Describe what happens to a sodium atom when it becomes an ion. So let's go over a couple of different things about sodium and this question. So the first key term in this question is ion. So an ion is a charged particle. Specifically, it's an atom after it's either lost or gained electrons. So an atom which has lost electrons becomes a positive ion. So you can remember it as if, so we know that electrons are negatively charged, and we start off, as we talked about earlier, with the same number of protons and electrons. So if an atom loses negative electrons, it's going to have more positive protons and fewer negative electrons. So there's an unequal number of positive protons and electrons, and we've got more protons. So it forms a positive ion. An atom which gains electrons forms a negative ion, which gain electrons, it can be one or many, forms a negative ion. Now let's talk about sodium and what we know about sodium. So sodium is a group 1 metal, and what you need to know about group 1 metals is that group 1 metals lose 1 electron, or metals lose electrons, and group 1 metals will lose 1 electron when it becomes an ion. So, well, we can say loses 1 electron. Okay, question 4. A student does an experiment to identify an unknown metal M. The student weighs metal M. Then the student adds metal M to a solution of copper sulfate. A reaction takes place forming copper metal, and we're given the equation M plus copper sulfate forms copper plus MSO4. The student separates the copper and then weighs the copper. These are the student's results. Mass of metal M is 8.10 grams. Mass of copper is 21.2 grams. How could the student separate the copper from the solution? So if we go back to the question, we are told that copper metal is formed. And if we look at the balanced equation, we can see that it's got some state symbols in brackets. These state symbols tell us what the state of matter of our products and our reactants. So in this case, copper has an S in brackets next to it, which tells us that this copper is solid. So let's annotate that. So this copper is solid copper that's formed. And in addition to solid copper, we have a MSO4 product that's made, and that has the state symbols AQ, which tells us it's a solution or solution. So if we draw a picture to try and visualize our final product, we're going to have this solution of MSO4, and we will have some solid copper. Let's just draw it at the bottom there. So that's solid copper that's formed. So we need a separating technique that can separate solid metal, in this case, from a solution. And the separating technique then that can separate an insoluble solid from solution, or from a solution, is filtration. It's the same technique you would use for sand and water. So sand is an insoluble solid. It does not dissolve in water. And this is similar to that situation. So you have copper solid, which is insoluble, and you can use filtration to filter that out, to separate that. Part B, calculate the relative atomic mass of metal M. And you're given the equation that you need to use. So relative atomic mass of metal M is the relative atomic mass of copper multiplied by the mass of metal M, all divided by the mass of copper. So let's try and highlight all the different bits of information that were given in the question and how it links to this equation. So if we keep reading, the relative atomic mass of copper is 63.5. So this relative atomic mass of copper, 63, is in our numerator here, in our equation, relative atomic mass of copper. So we're going to highlight that in the same color. Then the next term in our equation is the mass of metal M. So mass of metal M was given to us earlier on in the question. So if we look above, mass of metal M is 8.10 gram. And lastly, we need to divide this all by the mass of copper, which was also given to us, mass of copper 21.2. So if we sub all of that in, we're going to do 63.5 multiplied by the mass of metal M, 8.10, divided by the mass of copper, 21.2. And this gives us 24.26 grams. Now we need to make sure that we read the entire question because we're told that we need to give our answer to 3 sig figs. So 3 sig figs would be 24. So that's 1, 2, and then the third sig fig or significant figure would be this number here. But we need to make sure that we consider the neighbor number there. So we have 0.26, which means we need to round up to 3 when we're giving our answer to 3 sig figs. So 24.3. Use your answer from part I and the periodic table to identify metal M. So if we have a look at the periodic table and we are looking up an element with the atomic mass of 24.3 or 24, the closest one to 24.3. So if you remember earlier, we discussed that the larger number on our periodic table always refers to the atomic mass. So we are looking for an element where the larger number is as close as possible to 24.3, and that is magnesium. So that means our metal M is magnesium. Question 5. Draw a labeled reaction profile for an endothermic reaction. Use the following labels on your reaction profile: products, energy change, and activation energy. So an endothermic reaction is a reaction that takes in energy, or you could say absorbs energy. So what does this mean and how does it affect our energy profile diagram? If our reactants are taking in energy during this reaction, it means our energy of our products is going to be higher or larger than the energy of our reactants. So when we draw our line for products, we need to draw it higher than our energy of reactants. And it doesn't matter how high. I've gone this high, so it's clear that it's much higher than the reactants. You don't want it too close to the reactants. So I've drawn for this, I've gone for this height. Then, as with all energy profile diagrams, you need to connect your reactants and your product line with a curve. So let's start at the end of the reactants and draw a nice curve to the start of our products. And to show that it is our products, we need to add our label in. So products, and tick it off so you know you've done it. The other 2 labels we need to add is the energy change label and the activation energy label. Energy change labels always begin in line with the reactants, and the arrow always points to the product. So we're starting, if I choose a different color. So we're starting in line with our reactants, So I'm going to start my arrow here. So that dotted line was just so I know I'm starting in line with my reactants, and I'm going to point directly up to my products. And we want to label that energy change. Sometimes we can use a symbol as well. So delta H. So this triangle means change in. So that's my energy change label done, tick. And then the last one we want to show is the activation energy arrow. Now the activation energy arrow always begins in line with the reactants again. And this time it will point to the peak of your curve. So the highest point on your curve. So the highest point on my curve is this region here. So that's where my arrow should end. And we want to make sure it connects in line as straight as possible to the reactants. And you always want to make sure your arrows are single-headed. So it's only got a head on one side. And that's it. Right, part B. The reaction between iron oxide and aluminium is very exothermic. So this means it's releasing lots of energy. Look at the equation for the reaction. Fe2O3 solid plus 2 aluminium, Al solid, forms Al2O3 solid plus 2 Fe, and that's an L, which means liquid. During this reaction, the aluminium is oxidized. Explain what is meant by the term oxidized. Now, there are a couple of different definitions, and you could write either one and you can get the mark. So either you can talk about oxidation in terms of oxygen, or you could define oxidation in terms of electrons. Some of you might have learned that. So in terms of oxygen, if something has been oxidized, it means it has gained oxygen. So gain of oxygen. If you wanted to, you could also define it in terms of electrons. And oxidation is the loss of electrons. So both of these are fine. You could define oxidation in either way. Most of you would have learned the one in blue, so gain of oxygen. The last part of this question, pure iron metal is produced in the reaction. Draw a diagram to show the bonding in a metal. Label your diagram clearly. So whenever you're drawing a metallic bonding diagram, always aim to draw at least 2 rows of minimum 3 circles to show each of your particles. I'm going to go with 4 just to be safe. So we're going to have 4 in one row and another 4 in my second row. Now these circles are representing positive metal ions. So I'm going to draw in a positive charge, and I'm going to label these spheres as metal ions. Now the other part of these of the metallic bonding diagram are these negative charges, which are the electrons. And there is a term that we use to describe these electrons, and that is delocalized. So these electrons are described as delocalized electrons. And the final question. So a student wants to produce a pure dry sample of the salt sodium chloride. The diagram shows the metal they use, and we have a lot of information in this question. So let's take it all in and read it all. So we're given the first image, which is the boiling tube. Okay, let's move on to the final question, which is a 6-mark question. A student wants to produce a pure dry sample of the salt sodium chloride. The diagram shows the method they use. So in a boiling tube, they already have 10 centimeters cubed of dilute sulfuric acid and 2 centimeters cubed of indicator. And they are adding 2 centimeters cubed portions of sodium hydroxide solution to the boiling tube. Then the reaction takes place, and they've taken a conical flask, they've got a filter funnel and a filter. Let's label it so we can keep track. So we've got a funnel, we have the filter paper, And we have the solution that was in the boiling tube is now being poured in to the funnel through the filter paper, and some solution is being collected at the bottom. Through the funnel, through the filter paper, and something is being collected in our conical flask. If we read the method to get some more information, the method the student follows: measure 10 centimeters cubed of dilute sulfuric acid into the boiling tube, add 2 centimeters cubed of indicator. Step 3, add sodium hydroxide solution 2 centimeters cubed at a time, up to 10 centimeters cubed in total. Filter the solution to remove the sodium chloride. The question is as follows. So describe the mistakes the student has made and how their method could be improved to produce a pure, dry sample of sodium chloride. So I would consider there to be 3 parts to this question. We've got describe the mistakes. Then we've got the second part, which is describe how their method could be improved. And then I would say the third part is we need to include how the student is going to produce a pure, dry sample of sodium chloride. So I would say that's 3 different things that we need to talk about. And I would lay out my answer in a table format. Okay, so let's firstly annotate this question to figure out what exactly is going on so that we can identify the mistakes and the improvements. So we have sodium hydroxide, which is a base, and it's being added to a boiling tube which contains an acid and some indicator. So this is another one of those generic equations I talked about earlier in question 1, which is acid plus a base reacts together to form a salt plus water. This is a neutralization reaction. That's the type of reaction. Now, if we go into the specific details, so our base was sodium hydroxide, and the salt that the student wants to make is sodium chloride. We will, in the process, make some water as well. Now, if we think about what acid we need, so if we want to make sodium chloride, we're going to start with sodium hydroxide. So that's where sodium chloride gets the sodium. So it comes from the base. The chloride part of the name tells us what acid we should start off with. So the acid we need in order to form sodium chloride is hydrochloric acid. So we can see the chloride and the chloric in the hydrochloric acid are similar. It tells us where the chloride actually comes from. So it's from hydrochloric acid. So we can already see one of the mistakes that the student made. They started off with sulfuric acid, so it's an incorrect acid was used. So we can jot that down straight away before we forget. So number 1, incorrect acid used, and the improvement would be to use hydrochloric acid instead. Use HCl, or if you want to write hydrochloric acid. Going back to the equation. So we start off with an acid and a base, and we form a salt and a water, sodium chloride and water. Or sodium chloride, which is the salt, is a soluble salt, which means it will dissolve in water. So what we form is a solution, which is a soluble salt, which has dissolved in water. Now, we cannot separate a soluble salt from a solvent using filtration. Earlier on, we looked at another question relating to separating technique. Filtration is used for an insoluble solid, which you want to separate from a solution or a liquid. The technique we want to use instead for a soluble solid from its solvent is either evaporation or crystallization. We can write crystallization. Crystallization. So the mistake is that filtration will not separate NaCl, does not remove NaCl like they thought it did, filter the solution to remove the sodium chloride. Instead, the student should use evaporation or crystallization and leave to dry to produce the dry salt. So here, via this bullet point or this section here, we've described the mistake, we've suggested an improvement for the method, and we've also talked about how to produce the dry sample. So we're going to leave this to dry, and the solvent will evaporate, leaving behind a dry salt. So that's actually point 3 ticked off as well. Let's keep going to see if there are any other mistakes and improvements. So when the student tried to filter or try to filter the solution, we also in that solution from the boiling tube, there was some indicator present as well. So not only did we have sodium chloride and water, we've also, in addition to that, we've got the indicator that was added, the 2 centimeters cubed of indicator. So if we want to produce a pure dry sample of sodium chloride, we need to remove that indicator from the solution. Now, that's not easy. So instead, what we could do is take a note of how much base we need in order for this acid to be neutralized, and then repeat the entire experiment again without the indicator. So you note how much base you needed for that indicator to change color. You note down that volume, and then you would repeat the experiment again, just adding the exact volume of sodium hydroxide that you needed. And this time you wouldn't see a color change because you don't have indicator. As a result, when you evaporate or crystallize the product, you won't have that indicator in your solution. So number 3, indicator is still present. So the improvement, as we discussed, let's get it down in words. So once you have calculated the volume required for neutralization, you would repeat the experiment without the indicator. Now, just to go over what I said earlier on. So once you have calculated the volume required, so the way the student would do that is the first time round, we've got our acid in our boiling tube, and we've got our indicator as well. Now in acid, assuming it's universal indicator, there are lots of different indicators you could use, but the one that's probably most common to you or most known to you is universal indicator. So in acidic conditions or in acid, the indicator will be red or as close to red, depending on the pH, so reddish, orangish. When you start adding the base, this color will start to change and you will approach green, at which point we know we have hit neutralization. So this tells you you've added just the right amount of base in order for your reaction to go from acid plus base or your sodium hydroxide to forming your salt and water. Now, what would happen if you continued to add base or more sodium hydroxide, you would end up in a situation where you have salt, you would have the water. So these are your two products. But in addition to that, because you continue to add more and more base, you would have some excess or extra base in your solution as well. So you'd have your salt and water product, but you'd added too much base. So that's going to be left over. That's going to continue to be added. So you'll have base in your solution. And since you've got your indicator, which I've forgotten in this diagram, so remember you've got your indicator in your solution as well, and you'll have your indicator that you added right at the beginning. This indicator will no longer be green because it's only green. Universal indicator is only green when it's neutral, when it's pH 7. If you continue to add base, more and more base, it's going to turn to a purple/blue color. So you want to make sure that you add just enough base to hit neutralization, and whatever volume that is the volume I was referring to here. Calculate the volume required for neutralization and repeat without the indicator. And there are other things you could say. So you could talk about adding smaller portions of sodium hydroxide or using fewer drops of universal indicator. But what we've written here is more than enough for 6 marks. So I'm going to leave it there.